Okay, so we looked at 16. We want to look at 16, and this is on page 215. And this is the square root of x plus y equals 1 plus x squared y squared. I think it's x squared y squared. Yes, it is. Okay, so we are asked to find dy over dx. Okay. What is my starting point? First of all, I'm going to ask you, what does that mean? We are asked to find dy over dx, and we have a piece of information here. We know that y is a function of x. If I'm told to find dy over dx, it's very clear that y is a function of x. There is no discussion there, right? Is that clear? Otherwise, you would have said find dy over dp, and then I would have said y is a function of p. Okay? So please remember that. Which means that, of course, y is not a constant. Y is not a variable, I meant to say. X is the variable, but y is a function. So I differentiate the left-hand side and I differentiate the right-hand side. Now, when I differentiate a function using the chain rule, what do I have to write on the left-hand side? Remember the definition or the differentiation rule. Function, the square root of a function prime is 1 over 2 times the square root of the function multiplied by the function prime. That's the rule, correct? Yes? Good. So then the left-hand side, please dictate. I have to differentiate the first quantity. In this case, it's the variable. 1 plus. Very good. Awesome. Good. Now the right-hand side, keep in mind, this is 1, a constant, plus a product. We have to use the product rule. Function 1, function 2. So then, can anyone tell us anything about the right-hand side? 1 prime is 0. X squared prime is, very good, 2x times y squared plus x squared times, let me refresh your memory on the formula f, I meant to write, f to the nth power prime is n f to n minus 1 times f prime. So we bring down 2, we multiply by y to 2 minus 1 times, indeed, times dy over dx. Now how do we continue? Well, we see that we have the variable, the only variable we have here is dy over dx. But I cannot take it from the inside, remove it from the inside of parentheses, so I have to first distribute this quantity, eliminate parentheses, and then proceed. So 1 over 2 the square root of x plus y plus 1 over 2 the square root of x plus y times dy over dx equals 2xy squared plus 2x squared y dy over dx. Is this okay? Is this okay? We're not there yet, but is this step understood? Every step, every little piece of it. Is that a yes or is that a no? Yes? Okay, so now remember, this is what we are after. We can bring this here next to the other dy over dx term and move this to the other side. And at the same time, I'm going to factor out dy over dx. So 1 over 2 the square root of x plus y minus 2x squared y dy over dx equals 2xy squared minus 1 over 2 the square of x plus y. Is this okay? So I moved this term to the right, it became negative. I moved this term to the left, it became negative, but I pulled out the dy over dx. Now we're almost done with this. Now please dictate what goes to the top. Right, 2xy squared minus 1 over 2 the square of x plus y, and this is 1 over 2 the square of x plus y minus 2x squared y. I will eliminate denominators. So if you want to multiply and divide, multiply the top and the bottom by this quantity, then I will get dy over dx is 4xy squared the square of x plus y minus 1 over 1 minus 2, not 2, 4. 4x squared y the square of x plus y. And this is it. Any questions here? Do we feel a little bit better about implicit differentiation? Do you think we need another example? Don't be shy, please. Are we okay? Can I talk about the derivatives of the inverse trig functions? We last time talked about sine prime, which is very good. We talked about cosine prime, which is excellent. We talked about tangent prime, very good. And we talked about cotangent prime, same thing, but cosecant. And then the last two are a product. So secant x prime is secant x times tangent x, and cosecant x prime will be negative cosecant cotangent. Okay, so of course we have 6 trig functions. I will only require you to remember 3. They're derivatives, only 3 of them. So we have f of x, which is arc sine x, or also sine inverse x. Please do not say that sine inverse is 1 over sine, because it's not. It's the inverse function of sine. The second function is arc cosine x, or cosine inverse x. And the last one that I would request is arctangent or tangent inverse. And these are the only 3 that I'm asking you to remember their derivatives. So arc sine prime is 1 over the square root of 1 minus x squared. Arc cosine x prime is identical but minus in front. And this is the function that I've been torturing you with a lot. Remember, that's one of the reasons why we remember the graph, right? So this is 1 over 1 plus x squared. That's all I'm asking you to remember. These 2 are the same. One of them has minus in front, and the derivative of arctangent. Of course, if we have arc sine of a function of x, prime. Can anyone dictate the derivative of this? Right, by the chain rule. Same thing, let's also look at arctangent of f of x prime. What would that equal to? 1 over 1 plus that function of x squared times f prime. Because here we should be writing times x prime, but why don't I write times x prime? Because x prime is 1. There is no need. But the correct formula should have x prime in there. But there is no need because it's 1. Okay, so let's practice this a little bit. So let's say 56.
Wait, so,
Yes?
the derivatives of each, like, of the things, if it has a c in the front, it would be negative, correct?
What do you mean by c in the front?
Like, sine, it would be positive. Cosine c would be negative. Tangent be...
Oh, I see what you mean. Yes. Yeah, but when we get to the hyperbolic functions, that's not going to be the case. So careful. Very good. So 56 on page 216. And that function is f of theta equals arcsine of the square root of sine theta. What if we take 20 seconds and work on this? Let's see what we get. What will this equal to? One over the square root of 1 minus, but squared, which is sine x, or sine theta in this case, times yes, because now we have to differentiate the square root, 1 over 2 the square root of sine theta times, very good, excellent, well done. Do we all agree with this? Yes? Okay, let's look at one more. Let's say 54. Same page. Y equals tangent inverse of x minus the square root 1 plus x squared. I'm losing my voice. Please do not assume that that is a -1 and bring it down in front and subtract 1 from the power. Be very careful. This is just a notation. So, go ahead.
So, for the derivative of arcsine, it would be 1 over the square root of 1 minus x squared. So would that be 1 minus sine theta squared?
You want to put, instead of this, you want to put theta squared?
Or sine squared?
But it's a square root that I have to square.
Oh, is it the square root?
But the argument inside of arcsine is the square root. So I have to square this. That's why I only get sine.
Okay.
Is that better?
Yeah.
And then times the square root of sine prime, which is 1 over 2 the square root of sine, and times the inner function prime, which is cosine.
Okay.
Better?
Yeah.
Perfect. Good. So now let's determine y prime. First, we will have to write 1 over 1 plus this whole thing squared. X minus the square root of 1 plus x squared squared times. We'll get back to that. Times what? Times 1 minus 2 the square root of 1 plus x squared and times. Very good. Let's see if we all agree with this step. Do we all agree with this? Yes? Yes? Okay, now let's try and clean it up a little bit. These two go away. Then I will try to square this and see what happens. So I have 1 plus the first term squared minus 2 times the first times the second plus the second term squared times the least common denominator here is the square root of 1 plus x squared. And this will be the square root of 1 plus x squared minus x. So let's see if we understand what I just did. I copied the 1, and I squared a binomial, sort of, but I had to have 3 terms. The first term squared minus 2 times the first times the second, plus the second term squared. Here I found that the least common denominator was the square root of 1 plus x squared. So I had to multiply this 1 by the square root of 1 plus x squared, and then minus x. Okay, so the numerator now is the square root of 1 plus x squared minus x. The denominator is the square root of 1 plus x squared. And here there is a 2 and another 2, so I can put a 2 in front. 1 plus 1 is 2, and I took it in front. X squared plus x squared is 2, but I took the 2 in front. And then this one is minus x, the square root of 1 plus x squared. Now, I don't know what could happen if I just rationalize the numerator and multiply. Maybe something would cancel out. Let me see if I distribute, if something nice happens here. Not really. So then I have minus x. Maybe if I distribute, maybe, and then rationalize, this will get us somewhere, but I'm fine with it. You can try if you want at home and simplify it. And if you want us to try, we can try. I don't have a problem with that. So I would initially probably just distribute and see what happens. And maybe these two start looking alike, and maybe if I rationalize multiplying by the square root of 1 plus x squared plus x, maybe something nice happens in there. I'm not sure. I don't see it. But it could. So the numerator will become just 1, because the x squared with minus x squared will go away. So the numerator will be 1, but I don't know what's going to happen here. Maybe something nice will. But, so let's vote. Do you want me to continue, or? We want to continue? You want to try? To see what if it's getting us anywhere? Okay, well. So if we do that, then the numerator is 1 plus x squared minus x squared, so this is going to be 1. And now the denominator, I'm going to multiply these two. So I get 1 plus x squared, and then plus x. Aw, thank you for saying that. Very nice. Very nice. Awesome. So see, by simply distributing this radical here, I got this piece, and this radical to x, and I got this piece, and this is awesome. See, they're identical. It's just that there is minus between those two. So then 1 over 2, the first term squared, minus the second term squared. Ah, that disappears, sorry. Well done. No more square root. Okay. So now we have 1 over 2. This is 1 plus 2x squared plus x to the fourth. And let's see what happens here. Minus x squared and minus x to the fourth. These two go away. Great job. 2, 1 plus x squared. Excellent. Look how nice. Very nice. So it really simplified nicely. Awesome. Any questions for me? Any questions? Okay. I would like to continue with another example in which there's like a word problem. So we see where implicit differentiation comes into play. We can talk about orthogonal trajectories if that is of interest. We can talk about finding the equation of the tangent line to a hyperbola. Any preference? Any preference? No preference? Okay, in that case, I will choose. Let's talk about orthogonal trajectories. This is important in physics, and it has other applications as well, so it's a good application. So here is a function f of x, and here is another function, let's say g of x. According to my graph, how many points of intersection do these two functions have? 1. If at that point of intersection I show that the tangent to g of x is perpendicular, doesn't really seem to be here, is perpendicular to the tangent at f of x, f and g are orthogonal trajectories. Okay? We may have families of functions. So here's a family of functions. And here's another family of functions. If at each point of intersection, if that happens, if at each point of intersection the two slopes or the two tangents are perpendicular, the slopes, the product is -1 in other words, then we say that the two families of curves are orthogonal trajectories of each other. Okay, so let's look at a problem. Let's say 65 on page 216, in which we are given x squared plus y squared equals r squared, and we are given ax plus by equals 0. Let's read the question together. Here it is. Two curves are orthogonal if their tangent lines are perpendicular at each point of intersection. Show that the given families of curves are orthogonal trajectories of each other, that is, every curve in one family is orthogonal to every curve in the other family. And then we can sketch a couple of them if you want. So I picked this one, the first one. So first of all, I have to make sure that these two curves intersect. So what should I do to see if they intersect? Because I have to show that at each point of intersection, they are orthogonal. So any suggestions? What is this? What am I trying to solve? This is a system of two equations. It's not a linear system. This is a quadratic expression. No, in this case, it's a circle. We know that. But it's a system of nonlinear equations. Good. What would you recommend we do? Solve the second equation for either x or y. It doesn't matter which one. Which one would you like to solve for? Okay, you want to solve for y, so then by equals negative ax. So y equals negative a over b times x. What will I do now with this value? Exactly. Plug it in the first equation. Absolutely. So I have x squared plus a squared over b squared times x squared equals r squared. Remember, now I want to solve for x indeed. I have y. I have to solve for x. A, b, and r are just constants. Good. So I will factor out x squared because I cannot combine them. And find the least common denominator to be b squared. So then b squared plus a squared equals r squared. So therefore x squared equals r squared, b squared over a squared plus b squared. I multiplied both sides by b squared over a squared plus b squared, so I can get x squared. And now I have to take the square root, and I get two different values of x. rb over the square root of a squared plus b squared. So how many points of intersection did we find? 2. Very good. Awesome. We found 2 points of intersection. I'm going to call them point A and point B. Can anyone give us point A and point B? It doesn't matter. The order is not important. They are the same. Exactly. RB over the square root of a squared plus b squared, or negative RB over the square root of a squared plus b squared. And y is the same. Negative a over b times x. I should have multiplied it first. I don't want to put it like that. Sorry. I want to multiply it. So when I multiply, remember y is negative a over b times x. If I multiply this by x, by negative a over b, I will simplify the b. So this number becomes negative a r, this one. Negative a r over the square root of a squared plus b squared. And minus should be right in front of the fraction line. Do we see that, or should I write it? I'll be more than happy to write it. Should I write it? Yes, very good. So y is negative a over b, and now I have to multiply by this x, which is rb over the square root of a squared plus b squared, and these two go away, and that's how I get the negative ar over the square root. Better? So one more time, a has coordinates rb over the square root of a squared plus b squared, comma, negative ar over the square root of a squared plus b squared. In the same way, I have to determine the y-coordinate for b. So the y-coordinate for b will be negative a over b multiplied by this, which is negative rb over the square root of a squared plus b squared. I will simplify, and this changes into positive. So this y will be AR over the square root of a squared plus b squared. A lot of work. So this is RB over, no, negative RB over the square root of a squared plus b squared, comma, AR over the square root of a squared plus b squared. Okay, after all this work, we only, you know what I meant. We only identified A and B, the two points of intersection. We didn't do anything else. Now we have to go back to our equations and do what? Remember, two lines are perpendicular if their tangents, the product of their tangents is -1, is if m1 times m2 equals -1, or if m1 equals -1 over m2. But how do I determine those tangents? I have to do something to these two equations. I have to differentiate both sides, and remember, y is not a variable, but a function of x. Very good. So I'm going to copy those two, because of course I ran out of room. So I copy them here. X squared plus y squared equals r squared, and ax plus by equals 0. For the first one, we differentiate both sides. What do we get? Can anyone dictate for the first one? 2x, very good, plus 2 dy over dx, awesome. And the right-hand side is a, b, and r are constants. Very good. The second one, please. A plus b dy over dx. I'm going to call this dy over dx number 1. And I'm going to call this one dy over dx number 2, but because they come from two different equations. They can't be the same. Maybe they can, but I still have to differentiate between the two. So when we solve for this, I get dy over dx equals negative x over y, because I have negative 2x over 2y, and I get negative x over y. That's number 1. From here, number 2, dy over dx number 2 will be negative a over b. Okay, so we have the derivatives, an expression for the derivatives of each. And now the question is, what do I do? I have 2 points. I have point A, RB over the square root of a squared plus b squared, comma, negative AR over the square root of a squared plus b squared. I'm going to forget about point B. I just want to analyze point A first. So, if I plug in x here and y in here, there's nothing I can plug in here. This is fixed. It's just negative a over b. There is nothing I can plug in there. But once I plug x in here and y in here, what should I get for these two slopes? The product of these two slopes to be -1. What should I get in here? Should be how much? It should be b over a. If I don't get b over a times negative a over b, it's not going to be -1, right? So let's see. So negative, the numerator is this, rb over the square root of a squared plus b squared over y, which is negative ar over the square root of a squared plus b squared. The denominators will go away. The negative with the negative will become positive. So I end up having RB over AR. So what is this answer? How much? B over A. Is this product -1? So I know now that at least at point A, which is one of the 2 points of intersection, at point A, the 2 families of functions are orthogonal trajectories. Any questions? Okay, I will have to repeat for point B. Where is my point B? At point B, I have to, at the top, I put -RB over the square root. In the denominator, I put AR over the square root. What do you think we're going to get? Any wild guess? What do you think we're going to get? Of course. Of course, that's what I expect. So let's give it a shot. So for point B, I'm going to copy it one more time. -RB over the square root of A squared plus B squared, comma, AR over the square root of A squared plus B squared. And I have to put x at the top. -RB over the square root of A squared plus B squared over AR over the square root of A squared plus B squared. So the denominators will go away, the signs will change into plus, the R with the R will go away, and as expected, the answer is B over A. So then, what do we conclude about these 2 families of curves? They're orthogonal. Each and every function with a function from here is orthogonal, and we say that they are orthogonal trajectories. So then, from here, x squared plus y squared equals r squared, and ax plus by equals 0 are orthogonal trajectories. So, in summary, what did we do? We determined whether these 2 orthogonal, families of functions intersect. That was the first task. We found 2 points of intersection. Then we determined the derivatives, and we plugged in the derivatives, the x and the y, from those points. It turned out that the product of the slope from the first times the product of the slope from the second at both points was -1. Therefore, the 2 families of curves are orthogonal trajectories. At any point of intersection, their tangents will be perpendicular. Okay. Any questions? Okay. Moving on to derivatives of log functions. 3.6. Derivatives of log functions. Okay, the simplest log function, natural log function, is natural log x. The derivative of natural log x is 1 over x. Now, what if I have a natural log of a function of x, and I want to differentiate this? What will I get? 1 over f of x times f prime of x or dy over dx. If you want to write it as dy over dx, that's fine too. It's correct. Okay. The most important idea here in this section is, which page am I on? 7, 8, 9. The most important situation here is this. Let's suppose I want to differentiate sine x raised to tangent x. This is my function. So I want to differentiate a function raised to another function, f raised to g. This is my task right now. What do you think I should do? You would say bring g down, subtract 1 from g, and differentiate f. The answer is never. There is no rule. Differentiation rule, right? For this situation. You cannot apply anything that we've studied so far. Now, if you have the square root of x raised to the third power, it's a different story. But this is not a function. So when you differentiate, it will be 3 times the square root of x to the second power times the square root of x prime. And that's what we discussed before. But this is a totally different situation. Nothing works here. And yet, we can determine the derivative of this function. And here is how. So I'm going to call y as being sine x raised to tangent x. And I want to first apply a mechanism to both sides, an operator to both sides, that somehow brings that tangent in front. And there is only one mechanism, only one operator that will do that. Which operator will do that? Absolutely. Absolutely. Only log will do that. So I'm going to apply natural log to the left, and I'm going to apply natural log to the right. I have to. The left-hand side is just natural log y. Can anyone dictate the right-hand side? Very good. Tangent x times natural log sine x. Awesome. Well done. Now, the next step. What do you think the next step would be? I still would like to find dy over dx. That's my target. Exactly. I will differentiate implicitly both sides. Awesome. So the left-hand side, please dictate. Yes, 1 over y, but times, because y is a function. Excellent job. Thank you. But now I have to be very careful because this is the product rule. Here I have tangent x times natural log sine x. So please dictate the next step. We differentiate the first function and we get times the second function plus the first function, but now I have to be very careful because I'm differentiating natural log of sine x. So indeed, 1 over sine x multiplied by cosine x. Great job. Is it done? No, it's not done yet. So notice that we did two things here. First, we applied natural log to both sides. Then we differentiated implicitly. This is called logarithmic differentiation. So I'm going to write the title in a minute, but let's finish this one up. And I'll say this was logarithmic differentiation. Ready? So now I have 1 over y times dy over dx equals secant squared x natural log sine x Can anyone tell us what this can be replaced by? Plus tangent is cosine, tangent is sine over cosine, times cosine over sine is 1. Right? Sine over cosine times cosine over sine is, it's tangent times cotangent. That's 1. Remember, we are solving for dy over dx. What should I do to both sides now in order to solve for dy over dx? Exactly. But I will replace it by the function. Is sine x raised to tangent x, and in brackets or parentheses, secant squared x times natural log sine x and plus 1. And that's the final answer. And now I let you choose. We need to practice this.
Sorry, so 1 over y is
So y is this function, sine raised to tangent. And we multiply both sides by y, so it appears here, right in front. Is that okay? Perfect. So please choose on page 223, 43 through 50. 43 through 50 on page 223. And yes, this is called logarithmic differentiation. Which one? 50 it is. So in 50 we have y equals natural log x raised to cosine x. So let's do it step by step. I'm waiting for you to tell me what to do. What is the first step? We need a mechanism that brings this in front. Very good. So then natural log y equals natural log of natural log raised to cosine x. And now we bring cosine in front. So natural log y equals cosine x times natural log of natural log x. These are two functions. Good. So we apply natural log because we could not differentiate a function raised to a function. We can differentiate a function raised to a power, but not a function raised to another function. Good. Next step. What do we do next? Very good. I'm ready for the left. 1 over y times. Do we all see that? Now you have to be very careful because you have to come up with a sum of two products. Sum of two products. Please give me the first one. This prime is times natural log of natural log x plus cosine x times, be very careful, we have natural log of natural log. We differentiate the outer function first. 1 over natural log x. And times we differentiate now the inner function. That's it. Awesome. Great job. Let's try and condense it a little bit. I will write it one more time as 1 over y dy over dx equals negative sine x times natural log of natural log x, and then plus cosine x over x natural log x. Final step towards finding dy over dx. Yeah, so I multiply by this, both sides, but instead of just writing y, I will copy natural log x raised to cosine x, and then I put everything else in brackets. So as negative sine x, natural log of natural log x plus cosine x over x natural log x. How do we feel about logarithmic differentiation? So it's basically implicit differentiation, but first we apply log to it. Please choose any other problem. I would like to choose problem 12. And then you choose another if you'd like. Would you like to work on another? Implicit differentiation with logarithmic differentiation? Yes, of course. Sorry, I didn't think for a second to put it up. So I want you to look at one of these in which we practice how to differentiate a log function. And then we have those in which a function is raised to another function. These are not those. In this case, it's just simpler or easier to apply natural log before you differentiate. But this is not a function raised to a function. All these are functions raised to functions. Which one? Any preference? Okay, if not, I'd like to go back to this problem number. Okay, let's do 45. Very good. So it's x raised to sine x. Very good. Let's work on 45 for a minute then. Let's see what we get. Good pick. So one more time, 45 is x raised to sine x. So this is 45. And after that, I'd like to go back to that 12.